what we often do is that the power that you want the system to generate drives the problem. You want to produce this much amount of power. How much heat do you need? How much fuel do you need? What's the condenser cooling water and all that sort of stuff? All flows, no pun intended, all flows from the power produced. So Q dot N is M dot F H sub RP, which is equal to M dot S times Qn. So now I can find the fuel flow rate. So let's say that M dot F is equal to 410.02 times Q dot N, which is 3237.54, divided by H sub RP. I just picked an average value for H sub RP. So this is just 43,000. It's a typical H sub RP value. Then we'll get that M dot F is equal to 30.87 kilograms per second. So this is the fuel flow rate that goes into the boiler. So here's the steam generator. It's receiving this amount of fuel to generate that amount of steam to flow through the turbine itself. So these are extensions, and often things are framed with this. And so look at example 311. It had to do with storage tanks. So if you go back and look in chapter 3, we were able to figure out how big the storage tanks would be if I knew this fuel flow rate. So you can do the same thing now. You can go back there and see. So there's an example, and you'll see where the numbers were that were given in that example came from. But you can figure out the storage tanks and all the things that we had talked about in the first course in thermodynamics. Now, let's look at the condenser a little bit more. So if I have the condenser, so here it is, and I have, we saw here we have state 3 and state 4, but I also have the cooling water. So I have the cooling water that goes in, and let's say that I have a mass flow rate of the cooling water. So I have a mass flow rate of the cooling water that goes in and out of the condenser. The cooling water will go through the tubes. These are shell and tube heat exchangers. Will go through the tubes and out, and the steam condenses over the tubes. And then Q dot out is equal to M dot of the cooling water times del H of the cooling water. And this is equal to M dot S times Q out. And so now I'll give you an example of what the H's are. So let's say at 20 degrees C in 1 atmosphere, H is equal to 82.91. At 35 degrees C, H is equal to 146.18. So these are H sub F. So you're going to check that out. Then what I can do is I can use this and solve for the mass flow rate of the cooling water. So the mass flow rate of the cooling water is equal to 410.02 times 2018.08. This is Q out, divided by 146.18 minus 82.91. And I find out that the mass flow rate of the cooling water is equal to 13.078 kilograms per second. That's a lot of cooling water flow rate. So this is 13,000, and we had a steam flow rate of this We have a cooling flow rate of that. And so that's why power plants are located often near water areas. So often, power plants located near rivers, lakes, ocean. And if you're inland, you could have cooling towers, so sometimes they use cooling towers. We've looked at cooling towers, so we know about cooling towers. So when we looked at cooling towers, there was a circulating flow rate that went in to be cooled. And so when we looked at cooling towers, that flow rate was this m dot cooling water that we have right here. And so these are the water sources, and so the water comes out at a higher temperature. So the water comes out at a higher temperature, and this can cause thermal pollution, but it can also be a positive. So one of the things near power plant discharges is the fishing is good, because the fish like the warm water. They get bigger, it attracts small fish, the big fish eat the small fish, and fishermen catch the big fish. And it also enhances shellfish. So a lot of times they'll have the warm water, speeds up the shellfish growth, and so it becomes a symbiotic relationship that we can have. And now, let's look at the actual components and how they might work. So if we look at the actual components, let's look here. And this is to give you a little more insight into how they work. So if I have the turbine, so I'll start with the turbine. So typically this is turning 5,000 to 10,000 RPM. And when I have the turbine, we're not really going to get into this, but if it's turning this fast and it's connected to a generator turns at a much slower RPM, so I have to have a gear system here that slows this down. So this comes in with essentially the kinetic energy is equal to 0. It's a low kinetic energy. There could be, the velocity out could be about 200 meters per second. And because the blades are spinning around, right? We have the blades in here. So they're whipping around. And so I need an exit velocity so the steam can get out of the blades. So very often there'll be a velocity leaving the turbine, which could be at this level. And delta PE is effectively 0, and any heat loss, Q, is equal to 0. The turbines are insulated, they're insulated, there's very little heat loss from them. So we don't have to worry about that. So this is the actual turbine, they're insulated. The inlet kinetic energy is usually very low, the outlet could be this high. In our ideal Rankine cycle, we often don't bother with this. We're just using isentropic, we're just assuming there is no kinetic energy, but actually there is. With the condenser, I mentioned before it's a shell and tube heat exchanger. And so we have the steam here, and we have the cooling water . So we have the steam go in, so it's a shell and tube heat exchanger. And we saw that since this is the velocity leaving the turbine, there could be that same velocity here, so we could have v is equal to 200 meters per second or less. But the velocity that leaves there goes into there, so in your condenser design, there has to be a design to slow this down, slow the kinetic energy down, the velocity down, etc. The velocity leaving is very low, so KE is essentially equal to 0. There's very little there. And so, anyway, that's a shell and tube heat exchanger. Now let's look at the pump. So if I look at a pump, so we have so you've looked at a pump, so the inlet velocity comes in here, so this is where the water comes in, it spins around, and it goes out here. So we have the inlet going in, increases in kinetic energy, slows down, increases in pressure, and we're assuming it's isentropic, so it's adiabatic and incompressible. And delta KE and delta PE are typically 0. So typically we have the change of kinetic and the change of potential energy are 0. And now the last one is the steam generator, and that's a little more complicated, so let's look at that. So I'm going to draw this big box. We're going to have, this is a steam drum. We're going to, and this is where the water comes in. So the water is going to come in from the pump. It's going to come in here, and then we have what are called downcomers. So we have the water goes down, and then the water is going to go up in terms of something called risers. So your water goes down, it's getting heated, so I have my Q dot is coming in, Q dot in, and it goes over this, and here are the products of combustion. So the water comes in, and now we have little bubbles. So now you come up, and it has steam being generated, and then the steam is generated. The steam comes out the top, goes into a superheater pipes, and so we have a superheater here. So the bubbles come out, they bubble up, boop, 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 they bubble up, they go out through the superheater, and then to the turbine. What we want to look at as well is that when we have the turbine and the pump, they have efficiency, so they're not truly isentropic expansion and compression. So for the turbine, so we have a turbine adiabatic or isentropic efficiency. And so if I look at this on a TS diagram, start at state 2, and ideally we'd go down to state 3, isentropic, and actually it'll go down to state 3 prime. Doesn't necessarily mean it's going in the superheat region, it just means that the entropy is increasing as it expands through the turbine. So as it goes through the turbine, comes in at state 2, and it's really leaving it at S3 prime. The pressure is the same, so P3 prime is equal to P3. The pressure is the same, the entropy is different, and the turbine efficiency is equal to W actual over W ideal is equal to H2 minus H3 prime over H2 minus H3 isentropic. Make that a smaller. Okay. So what is going to happen in problems is that we have to find the ideal, use the efficiency to calculate the actual. And so we'll need the actual state. And similarly with the pump. So, what the second law told us in chapter 8 is that the entropy will always increase. So when I look at this, and we now have the process going like this, 1 prime is located here. And so the pump efficiency is work ideal over work actual. So work ideal is H1 minus H4 isentropic over H1 prime minus H4. So this is the value that we found from where we found that V delta P, where we assumed Q was equal to 0, etc., because it was an isentropic process. So we have that. So example 15.2 indicates finding actual values using eta sub t and eta sub p. So you can look at that. There's no sense in my repeating it. It's done very well. Patting myself on the back. Maybe I should pat my co-author on the back. I don't know which of us did that. And so now for homework, 15.3, use 10 MPa. 15.7, 15.9. One of the things with the homework problems, and I'll mention this again, is that if you're going to use the pressure that you can find in the tables. The homework problems were set up for a variety of pressures, such as 8 MPa. Well, in the superheat tables. The superheat tables don't have 8. They have 5 MPa and 10 MPa. So you pick the one that's closest and use that. And the answers will be pretty close to what is in the solutions manual or in the back of the chapter.